This is Chemistry 104, the introduction to the chapters 1 and 2. I know it's a little bit confusing since the commentary and the chapters both use the term part, but keep in mind that this is for the chapters 1 and 2, part 3 commentary. In this we focus on alkene addition. Let me go ahead and use my yellow highlighter. The alkene addition reactions. Here we have a classic example of an alkene addition reaction. And these are reactions you're going to have to memorize and then apply on future quizzes, exams, tests. So to start us off, these are the reactants that I'm highlighting. This right here is a reactant containing a alkene, and then this is a diatomic molecule that I'm going to be adding in to the alkene. Hence the term alkene addition, since we're adding another substance into an alkene, creating one general substance. We focus, as far as tests go, on reactions. So the reactions show the before and after. The before and after. So think these are the substances that are going to react before, and then this is the reaction arrow. So basically we're going to shoot forward in time, space-time travel, and then this is going to be our results afterwards. So in this case over here, products are the substances that are going to be produced afterwards. Okay. So in this case, this shows the alkene bond was broken and two atoms from the diatomic molecule were added in. We keep it generic as A, B. Here, let's see another example over here. Starting alkene, here is my molecule I'm going to add in. Again, this is before. Let's go forward in time. Forward. And here is our final product. That's the substance produced after. Okay? So, notice how I can write the newly added atoms either on the bottom or I can add them on the top, as I did in this generic example above here. So you have two different choices. Both are considered correct. So sketching-wise, you do have a lot of leeway. You can put both of them on top, both of them on bottom, or maybe one on top, one on bottom, whichever is easier for you. The bad news is you see it written like this both ways, both in the slides and in the book. So you kind of have to get comfortable with it. These are, so you can think of them as being the same thing. Let's move on. Up here we have the general reaction again. Instead of A, B, we use the term XY. Notice how I put the diatomic molecule, I added it into the pi bond on the bottom. And then here is my after picture showing the final product. Notice the double bond is broken in the after picture, leaving only a single bond. And when they broke apart, one of the electrons formed a brand new covalent bond with X, the other one formed a brand new covalent bond with Y. Again, all 5 reactions always have this same pattern going on. So we try to keep it pretty simple for you. Now, is this how it actually happens, where before and then they come close together and then like a bad science fiction movie, all of a sudden, then they magically form this? No. In truth, the reaction is actually more like a step-by-step process. So you can think of a mechanism as the step-by-step or the frame-by-frame movie motion of a reaction. So let me go ahead and give you an example. Here in this picture over here, I have a reactants. This is very similar to how I would actually give it to you on the exam. And this reactant right here is actually going to move over here. And if this were a mechanism, we would actually see these hydrogen molecules moving over here. And then in a separate step, we would actually see a brand new hydrogen bond forming. So in this case, it's a little bit hard to do with this software, but there we go. Okay. Oops. I added too much. See? It's not easy for me either. I deleted everything. Alright, don't panic. Let me go ahead and change this bond right here for right now. Stretch it out. So this is a brand new hydrogen that I just added in. And then let's go over here. Yeah, this is a brand new hydrogen that I just added in. And then I'm going to go ahead and remove the double bond. Okay. This would be the real-time motion. What scientists do is they compromise. Rather than showing the movement of the atoms bonding, what they do is they like to show nice, pretty pictures. So going back to our original example, what they'll do is they'll show a reaction pushing arrow. And in this case, the pi bond is going to go ahead and form a brand new covalent bond over here. So this is a pushing arrow. And then as soon as this forms, you have a empty carbon. Let's go back to our slides. And for something I'm not going to be testing you on, I've really spent a lot of time on this. But here we see in blue an electron pushing arrow, and it tries to show the real-time bond formation of this particular atom right here. As this atom bonds, we see the arrow showing a real-time bond breakage in the electrons temporarily. Let's go to step 2. The bonds temporarily form a brand new lone pair. Now in step 2, what actually happens is, because a carbon is missing, and if you notice I had so much trouble adding or taking away carbons because the program didn't like breaking the 4-bond rule. In nature, however, as long as it's instantaneous, the nature will actually break the 4-bond rule. So right now you can see it's missing a bond. Because it's missing a bond, it actually forms a temporary positive ion called a carbocation. This carbocation is positive. This newly lone pair atom, which happens to be negative, is an anion. And what happens? Opposite charges attract. The positive and negative come together. And this is shown by this electron pushing arrow forming a brand new covalent bond. In this picture over here, we finally have the after product, and this is a crude example of a mechanism showing the step-by-step, real-time, bloody action of a alkene form a brand new bond. I could show you a nice 3D animations that they put together in the past, but I don't want to spend any more time on this because I am not testing you on mechanisms. What we're going to do is show you the reaction, the before and the after. Now, because I'm only showing you the before and after, you're going to have to take a lot of these reactions on faith that they work. If you're curious during our in-class discussion or lab times, I'll be happy to show you the fancy pants mechanism of how they actually interact and come together. But for right now, you just have to memorize the patterns. Memorize the patterns. Let's go ahead and go to the next slide. Up here we see a nice reaction you have to memorize. Memorize. Down here we see the fancy pants mechanism showing the step-by-step reaction of hydrogen molecules bonding. Consequently, this is called a hydrogenation. See how clever we are when we come up with our names? Hydrogenation reaction. Down below, you don't have to memorize. Scratch that out. If you want to look at it later on for understanding it, great. But let's focus on the top. Here's before. There's the alkene. Here are the hydrogen atoms. And then here's after. The bond's going to go ahead and... Let me go ahead and use a different color. The bond's going to go ahead and break here and here. And the bonds are going to break here and here. The hydrogen on the left is going to go to this carbon. The hydrogen on the right is going to go to this carbon. And voila, we have a single bond carbon-carbon with two hydrogens attached. Memorize how to come up with a pattern for the product. You'll notice miscellaneous substances right up top. This is where we like to put our conditions for speeding up the reaction. This right here is a catalyst. Keep in mind these two molecules are going to be floating around, and in order for them to react, they need to bump into each other, kind of like billiard balls on a billiards table. So the platinum acts like acts as a piece of flypaper, and basically it's going to go ahead and hold on to one of the molecules, making it easier for the other molecule to actually bump into it. If you understand that, great. If you don't, you can ask me during class. I'm not going to be testing you on the catalysts. Just know that if you see one, that's most likely what it is. It could be a catalyst. Another thing it could be is the solvent. Some of these require special solvents in order for this reaction to work properly. Again, you'll be given the reactions, and if there's a catalyst, great. If not, don't worry about it. You will have to predict what the product is. That's the most important thing. Moving on. Here is another two-step mechanism. This shows an example of a heterodiatomic molecule. Hetero meaning the atoms are of different type attaching. Great if you want the fine details, but no, I'm not testing you on this. Let's move on. Here is a slide I am going to test you on. Memorize these 5 reaction names. You'll be responsible for predicting the products for 4 of these. The other one, I could test you a general question, but I'm not going to actually have you predict it. These are much harder. Here is the general reaction, and voila, I beat this to death. You should be able to figure this out in your sleep now. The first one is hydrogenation. That's because we're adding in hydrogen gas molecules. Hence, that's where we get the name. Here is the catalyst, as well as the other conditions required for this to occur. If you see these reactants up front, you need to memorize this is a hydrogenation reaction, and it's going to add in 2 hydrogens. What? Well, here you have a choice. Because it's line angle, you can choose to show or choose to hide the newly added in hydrogens. You can write it like this here, or if you want to use a combination of line angle and expanded, using my super pen, you can always write it like this. And here I actually show the expanded hydrogens actually attaching. Either one would be acceptable. For the first set of quizzes and the first exam, read the question carefully. If I say sketch any, use any sketching structure type, then you can use a combination of both. You can use one, you can use the other. If, however, I say the words you can only use line angle or only use condensed, then that's a big hint. That's the only one you can use. For these reactions, I will give you the option of using 1, 2, or a combination of both of them to represent the final product. And this is actually what scientists do when we come up with reactions. If we have a choice, we usually like to use two of them together to emphasize the part of the product that the reaction occurred. Moving on. Here is halogenation. Hey, what do you think we're adding in? Duh. We're adding in halogens. Again, the bond breaks and it forms a saturated hydrocarbon derivative with two brand new halogen atoms attached. I could change this and add in Cl2 for chlorine gas. I could add F2 or I2. I could write it like this where you see the bond, or I can write it in this example on the bottom as the molecular formula, Br2 or Cl2. So make sure you recognize these starting reactant formats, and of course you'll have to predict the products over here that I'm currently highlighting. CH2Cl2, this is actually a special solvent and helps speed up this reaction. So you can think of it as kind of a catalytic solvent, if you will. Do you need to know that? Well, I'm going to give you the starting reactants anyways, so if it's there, great. If it's not, ultimately you'll have to recognize the reactants to the left of the reaction arrow to figure out what the desired product is. Although these are nice, they're not really important for you to memorize at this level of chemistry. Moving on, hydrogen halide. Well, this should be a big hint. One of them is going to be a what? I'll give you 2 seconds. 1/1000, time's up. One of them is going to be a hydrogen. The other one's going to be a, what do you think? Halide. In this case, we'll just pick bromine. Here is my example over here, HBr. One of these atoms is going to receive a hydrogen. The other one's going to receive the bromine. Here's a problem with diatomic molecules, heterodiatomic molecules. One of them is different, and so if we have a structure like this, this could make all the difference. Do we put the hydrogen to the left, or do we put the hydrogen to the right of the alkene? Consequently, we have two different structures that I'm highlighting. Which one is correct? Keep in mind, nature sometimes can be really picky, and it prefers one structure over another. In this case, it actually prefers the structure on the left-hand side, not the structure on the right. I will give you a very quick 10-second reasoning why, but you're not tested on the reason why. You are tested on the Markovnikov rule and apply it. So let me give you my quick 10-second reason why. We're going to have to go backwards in time to slide 4. Let me go ahead and erase all of this junk that I have on there right now. In slide 4, it turns out that if we look at the mechanism, the frame-by-frame motion of the reaction occurring, as soon as we added in the hydrogen over here, we have a temporary positive charge called a carbocation. It turns out that we need to have this positive charge on a more substituted carbon. So that way, the nearby carbons will actually come in and donate their electrons to temporarily in order to balance out that positive charge. So the more carbons that are surrounding the carbocation, the more stable it is. And therefore, the bromine is going to go on that more substituted carbon. If you were to have a carbocation on a N carbon, well, it'd have less carbons surrounding it, so therefore it's not as stable. That's the 10-second explanation using a mechanism. You are not required to understand that and explain it on a test, but feel free to ask me in class more detail on that. Let's go forward in time so I can tell you what you need to understand. You need to memorize Markovnikov's rule, where we need to pick the proper molecule. Regioselectivity means nature prefers one product over the other. We need to apply Markovnikov's rule. So here's Markovnikov's rule. The rich get richer. The rich get richer. Instead of dollars, we're going to be counting hydrogens. So, using my highlighter, which one of these carbons on the alkene carbons, let me say that again, which one of these alkene carbons, and I'm going to highlight the alkene carbons, which one is richer when it comes to hydrogens? The one on the right or the one on the middle? It turns out the one on the right, ding ding ding, is going to be the richer one. Let me go ahead and change colors because I'm getting bored with this color. Let's go here. Yeah. Blue. Blue is better. So in this case, this carbon right here is going to pick up the hydrogen. Consequently, we attach it showing the covalent bond like this. So the rich get richer. If it already has 2 hydrogen, then it's going to get richer, and now it has 3 hydrogen. The poor carbon over here, that actually then picks up the bromine. So apply the rich get richer rule. Moving forward, here is a hydration reaction. Think hydration, hydrate. What happens if you're supposed to get hydrated? Whenever you say you need to hydrate yourself, like they say in the military, that means you need to have extra water taken in. You need to drink more water. When we have a hydration reaction, we're adding in water. This actually is a little bit tricky. I like writing it like this, but if you have a starting reactant like this, then my advice is to rewrite it. Let me go ahead and use red for this example. Rewrite it in this form right here. Let me go ahead and use my magic red pen. Come on, magic red pen. Rewrite it in this Lewis structure form right here. Can everybody see how it's written like this? Now, let's go ahead and categorize it. We have 2 parts. We have the hydrogen and we have the hydroxide. It turns out that nature will sit there and, let me go ahead and use my blue pen. Nature will break this apart. And the carbon, which is richer, in this case the carbon on the right side, the rich get richer, is going to pick up the hydrogen. The carbon on the left side, and I might as well use green. Green is good. Is going to pick up the leftover hydroxide. I'm not going to show you the mechanism on this, just take it on face value. The hydrogen is going to get on the richer carbon. So in this case, it goes ahead and creates what's called an alcohol. If I give you the slides after this, you'll be responsible for not only naming the sketch, but also naming the compound itself using the UPAC naming scheme. So this case is called a 2-propanol. The common name on this is isopropyl alcohol, the rubbing alcohol that we put on our achy fingers from making these all day. If there were to be scratches, never mind. Anyways, if you notice over here, we have H2SO4. Ignore this. This is a catalyst. This speeds up the reaction. again, I'll either give this to you or I'll either give it to you with the starting reactants or I won't. It doesn't matter to me. But you will have to predict the product. So make sure you can predict the product over here. Down here is another example. Again, the rich get richer. I'm just going to use any pen at this point. This carbon picks up the hydrogen, and then this carbon over here, the poorest of the poor, pick up the hydroxide. Hence, you draw this structure right here.